Have you ever thought about this? In the world of wireless tech, some of the absolute best signals, they come from recipes that look nearly identical. I mean, how is that even possible? Well, today, we're going to dive into a really cool paradox that's at the very heart of the Wi-Fi, 5G, and radar systems you use every single day. Okay, so let's kick things off with a little puzzle. Take a look at this. On the left, we've got two signal recipes that are, they're practically twins. And on the right, you've got two that look totally different. Now, what does your gut tell you? You probably think the ones that look different are going to create the more unique signals, right? Well, hold that thought, because the answer is probably not what you're expecting.
So to really get why that puzzle is so tricky, we got to talk about a huge challenge in wireless technology. I'm talking about everything from your Wi-Fi router at home to the 5G tower down the street. The whole game is about cramming a ton of signals into the exact same space without them all just turning into a jumbled mess. So engineers have this job of creating this big, happy family of signals that can all play nicely together without stepping on each other's toes.
Okay, so there's a fancy word for this, orthogonality, but really you can just think of it as a signal's ability to stand out in a crowd, its uniqueness. And we can actually measure this using something called a correlation value. It's pretty simple. If two signals are identical, they get a score of 1. If they're completely different, totally distinct, they get a 0. And that's the magic number. The goal for engineers is to get that correlation value as close to 0 as humanly possible. All right, so how do they do it? How do engineers actually make these unique, non-interfering signals? Well, it all comes down to giving each one its own special recipe. The technical term is a frequency law, but it's basically just a mathematical blueprint, a set of instructions that tells the signal exactly how its frequency should change from one moment to the next. And remember those shapes we saw in that first puzzle? Yep, each one of those is a totally different recipe. Now, what's really interesting is how they find the perfect set of recipes. You might think it's just some single stroke of genius, but it's not like that at all. The research shows it's a long, careful journey of trial and error, and a whole lot of refinement. It's basically this big, systematic loop. First, engineers dream up dozens of these mathematical shapes, or recipes. Then they use those to cook up the actual signals. After that, it's like a big tournament. They pit every single signal against every other one to measure just how similar they are. They chart it all out, see what works, keep the winners, toss out the losers, and then they do the whole thing all over again, hoping to build an even better team of signals. And this is where things started to get weird. The first surprise. You see, early on, engineers did the most logical thing. They tried using recipes that looked completely different from each other. Makes sense, right? But look at these results from just their second attempt. The sawtooth and cosine hump recipes. They created signals with a correlation of 0.41. That is way, way too high. Remember, the goal is 0. So the obvious, intuitive approach? Total bust. Okay, so after all of that grinding, methodical testing, something completely unexpected started to emerge. A pattern. And this is going to bring us right back to that question I asked you at the very beginning. The results pointed to this really deep, really counterintuitive truth about how these signals actually work. Get this, it turns out our gut feeling was totally 100% backward. The research proved without a doubt that the signal recipes that look the most alike are actually the easiest ones to tell apart in the end. I know, it sounds crazy. Let's look at the data that proves it. Okay, first up, let's just look at the recipes themselves. Take this pair here, the Gauss and exp shapes. They have a correlation of 0.9975. That is so incredibly close to 1.0 that mathematically, they're pretty much identical. If you were to graph them, you'd have a hard time seeing any difference at all. But here's where the magic happens. When we go and measure the final signals that are actually created by those nearly identical recipes, the whole story flips on its head. That exact same pair, Gauss and exp, now has a correlation of just 0.0675. It's incredible. They went from being identical twins to being complete strangers. Think about that for a second. That's a staggering difference. The similarity between these two signals dropped by more than 93% just in the process of turning the recipe into the final product. It's almost like alchemy, a truly magical transformation.
So what in the world is going on here? How can two things that start off so similar end up being so radically different? To really wrap our heads around this, let's check out an even more extreme example that the researchers came up with.
Okay, to really push this idea to its limit, the researchers did something they called the mirror test.
It's clever. They took one recipe, X plus, and they created its perfect opposite, X minus. It's literally an exact vertical flip, a perfect mirror image of the original. So you couldn't get two recipes that are more perfectly and symmetrically related than these two.
And the results are just, wow, absolutely stunning. The recipes themselves, because they're perfect mirror images, they had a correlation of exactly 1.0. But the final signals that came out of them, get this, a correlation of just 0.08. So a perfect mathematical relationship led to almost perfect distinction. This, right here, is the very heart of the paradox. Let me give you a simple analogy to make sense of this. Think of the frequency law or recipe as a super detailed set of driving directions. You know, the kind that tells you your exact speed and direction at every single moment of a trip. The final signal, in this analogy, is determined by its phase, which is kind of like your car's final position on the map after you've followed all those directions. Okay, here's the absolute key to the whole thing. The final shape of the signal gets figured out by adding up all the tiny little changes in the recipe, moment by moment, over the entire time. It's all about accumulation. And what that means is that even tiny, microscopic, practically invisible differences between two sets of driving directions, when you add them up continuously over the course of a whole journey, they'll lead you to two massively different final destinations. That is the secret sauce. So once the researchers understood this paradox, they could actually use it to their advantage. They were able to assemble what you could call a dream team of signals, a really powerful toolkit that's essential for modern technology. And here they are. After seven full rounds of testing and tweaking, this was the final winning team. We've got 10 signals here, and each one is born from a unique mathematical law, and they were all chosen for one reason: their amazing ability to live together in the same space without causing chaos. And just look at this final matrix. See that sea of dark squares? That's showing the correlation between every single pair on that winning team. Almost every single one of those numbers is way below 0.15. That, my friends, is the signature of a high-performing, low-interference system. This is what success in this field looks like. So why does any of this matter to you? Why should you care about this weird mathematical paradox? Well, because this very principle is what allows dozens of Wi-Fi networks in your apartment building to all work at the same time. It's what lets 5G handle thousands of people on their phones in a tiny area, like a stadium. It's what lets advanced radar systems tell the difference between a bird and a plane. It's simple. Better signals mean better, faster, and more reliable technology for every single one of us. You know, this whole signal paradox is just a fantastic reminder that the technology we hold in our hands every day is built on these incredibly elegant and often really counterintuitive mathematical ideas. It really makes you wonder, doesn't it? What other hidden complexities are just humming away right beneath the surface of the things we use every day? It's something to think about.